The second type of chromatography that you need to know about is called gas chromatography, or sometimes gas liquid chromatography. And we'll see the significance of the liquid in a minute. So GLC, gas liquid chromatography. It's similar in terms of the absolute basic principles to TLC, in the sense that you have a mobile phase trying to drag substances through the apparatus and a stationary phase trying to hold them back. But that's about as far as the similarity goes. So the detail of how the method works is completely different. And what's really important is that you don't get them mixed up. Okay, so you've got to make sure that you have a clear understanding of the two techniques and make sure you use the right terminology for each one. Don't get them confused, because that is one of the biggest issues generally with chromatography. So let's have a look then at how a gas chromatograph works. So this is a very simple, crude picture of a gas chromatography setup. What you have is this long tube, and it's typically coiled up like this, and in fact not just coiled once but coiled many times, simply because it's a very long tube. It can be tens of meters long, and obviously it's inconvenient in the lab to have it all stretched out, so you coil it up so that you can fit it inside this box. And the box is an oven, for reasons we'll talk about in a minute. So you typically see it drawn as a coiled tube like that because that's physically what it's like. But as I say, the coiling is there simply because it has to be small enough to fit in the lab. And through this tube you push a gas. And the gas can in principle be anything, but it wants to be something that isn't going to react with the sample that you're analysing. So you want something unreactive, like, for example, nitrogen or argon, all sorts of things. But you want an unreactive gas, and that is going to be your mobile phase. So just as in TLC, you had a solvent rising up the plate and trying to drag substances with it. Here you have a gas with a bit of pressure behind it to force it through the tube, and it's also going to try and drag the substance with it, so it functions as the mobile phase. The sample is injected here, so near the beginning of the tube, so there's just a syringe which pokes into the oven and allows you to inject a sample into the stream of flowing gas. And of course the reason that we put it in an oven is that you want the substances in the sample to vaporize. So that they will go into the gas phase and get carried through the column by the gas, which is the mobile phase. And so the temperature of the oven is going to depend on what it is you're trying to separate, but it needs to be hot enough that the substances you're interested in will vaporize when they get into there. That's the idea. So if that was all there was to it, then of course all that would happen is the substances would vaporize here and they'd all get carried along at the same speed through the column, and they'd all emerge out at the other end at the same time, and it would all be a pointless exercise. So what you need is a stationary phase, something which is going to slow them down to different extents on their journey through the column. And the stationary phase is a lining of this tube. Okay, so on the inside wall of the tube, and I won't draw it all the way around, but lining the inside of this tube, what you typically have in a gas chromatography system is a layer of a non-volatile liquid. Non-volatile obviously is important because if it's a liquid, you want it, if it's going to be the stationary phase, it's got to stay there, and if it was volatile it would just vaporize in the oven and disappear into the detector, which would be pointless. So it's typically a polymer, something with really quite a high melting point, so it's a non-volatile liquid lining the column. And that's the crucial thing, because you can picture that what's going to happen is that as our substances go through the column, they're going to be constantly, moving around in random directions, and if they hit the layer of liquid on the outside, there is a possibility that they will dissolve. And depending how soluble they are in that liquid, they will stay there for various lengths of time. Eventually, they will always vaporize again, and then they'll get carried further through the column. But the point is that every time one of these molecules of the substances you're analysing, every time one of those molecules dissolves, that stops it in its tracks, because the liquid isn't moving. So while it's dissolved, it stays stationary. Then it may go back into the vapour phase and get carried further through the column, but then it will get dissolved again and slowed down some more. And the more soluble the substance is, the more time it will spend becalmed in the liquid phase rather than moving through the mobile phase. So the non-volatile liquid lining the column is the stationary phase. Okay, so what's really important is that you see the difference from TLC. That in TLC you also had a liquid phase, but in that case the liquid was moving. So the liquid, the solvent, was the mobile phase in TLC because it was moving. Here you also have a liquid whose function again is to dissolve the substances being analysed depending on their solubility, but here that liquid isn't moving, it's sitting statically lining the column, and therefore its job is the opposite, it's to slow down the movement of the substances through the column. So that's our stationary phase, that's our mobile phase, and what it means is that while the substances are all introduced into the column at the same time, they will reach the other end at different times. And we have a detector. You don't need to know anything about how the detector works, but the detector can tell when different substances arrive at the end point. So what you end up with is a gas chromatogram, which is a kind of graph that looks like this, where in effect this is amount of substance on the y-axis, and this is time, and specifically we call it the retention time. Okay, so the retention time is the time between when the sample is injected here and when a particular substance arrives at the detector. Okay, so and that can be, depending on how long your tube is and how fast your gas is flowing, that can be tens of minutes. Okay, so we're talking about a long journey that these substances have to take. So different substances have different retention times, and so what you get is a trace that might look something like this. Okay, so what that represents is that in this case we've got at least 6 substances. Remember, the at least is because it's possible that 2 substances might have the same retention time, so any one of these peaks could conceivably not be from a single substance, it could be from a mixture where they just happen to have the same retention time. But if you compare this with TLC, the really important thing is that these peaks are extremely narrow in comparison, so that, you know, in this case we've resolved at least 6 substances. If you look at examples of TLC, for example, if you Google TLC of red wine, that's quite an interesting one to look at. You can find pictures like that, but you can see that there are literally dozens of substances separated. Because these peaks are really narrow, you get much better resolution, much better separation of individual substances in gas chromatography than you do in TLC, and that's why it's such an important method. TLC is fine for a mixture which might only have 2 or 3, you know, up to maybe half a dozen substances in it if you're lucky. But if you've got a sample with dozens of substances in it, or substances which have closely similar structures, so separating them is very difficult on TLC, gas chromatography is your answer. So it's a much more powerful method, but it comes at a price. A TLC plate costs, you know, a few pennies. A gas chromatography setup costs, you know, thousands of pounds. So, you know, you invest in this when you need it, when you have to be able to analyse complex mixtures. So let's think about what it means. So if we label these substances, you know, A, B, C, D, E, F, and we think about why does F have a much longer retention time than A, what does that mean? Well, remember the process is that all the substances enter at the same time and they start flying through the column in the gas phase. The fact that F takes longer to come out means that its journey through the tube has been interrupted more of the time. And what interrupts it is dissolving in the stationary phase, because as soon as it dissolves, it stops moving. So what we can conclude then is that F has the longest retention time out of these substances because it is the most soluble in the liquid stationary phase. Okay, so you've got to make sure that you can see that that makes sense, and remember to explain things in those terms. The more soluble it is, the more easily it falls out of the moving gas phase into the not moving liquid phase, and therefore the longer it takes to finally arrive at the detector at the other end. So those are the basic principles of the method. When you talk about it, therefore, you talk about solubility of the substance in the liquid stationary phase. More soluble it is, harder it finds it to make its way through the column, so the longer the retention time will be. So you don't talk about RF, it's different from TLC. Retention time is the analogous factor.